My name is Lindsay Hoffman. I am a third-year student here at UC. I'm in the environmental engineering program. Um, I was born and raised here in Cincinnati, although I would love to move somewhere warmer. It's a little too cold for me here. Somewhere more tropical would be nice someday. My interests include arts like drawing and painting, and just recently I've been into making pottery. I would like to use this creative side of myself in environmental engineering to hopefully come up with some new ways of helping waterway systems or air pollution and that sort of thing. I'm not really sure which direction I want to go yet, but would hope to make a difference in that way. Um, I have a lot of plants, which I enjoy taking care of. As you can see, there's many. I also have a cat who follows me around like my shadow, but I love her. Um, for this class, I would really like to get an A, and to do that, I will definitely need to brush up on my coding skills more than I already have and learn more about it. I will also put in a great deal of effort in making these videos and really teaching myself the material from Carlos's videos and being able to reiterate that information in my own videos. So today we'll be discussing how to get to the triple point of water using basic kitchen supplies. We're going to start with this phase diagram here, and we're going to use this to predict how water will behave at different temperatures and pressures. So you see here along the x-axis we have the temperature in degrees Celsius, and along the y-axis pressure in atmospheres. So you can see we have three different regions. This region, water exists as a vapor. This region, water exists as a liquid. And this region, water exists as an ice. Our goal is to get at the triple point where water is 0.01 degrees Celsius and where all three phases exist at the same time. So we're going to begin by looking at a system where we have liquid water, and just above that we are going to have vapor. Water vapor exists just above the liquid, and then we are going to have air above our system. So the issue here is that because there is air in our system, we cannot use the phase diagram to predict how water is going to behave. But all we have to do is get rid of the air from the system, and then we can use our phase diagram. So to remove the air from our system, all we have to do is heat our liquid. So as we heat the liquid, it is going to give us more and more water vapor, which is going to drive our air up and out of our system, all that vapor pushing the air up. At this point, all we have to do is seal our system so that it leaves us with vapor and liquid. So now, if we look at our phase diagram, we are sitting right around this point along our liquid and vapor line, where liquid and vapor water exist at the same time. So our goal is still to get at the triple point here. We need to move down along this axis and down along this axis, so we need to lower the temperature from where it's at. To do this, all you gotta do is throw it in the freezer, and when we do that, our heat is going to be leaving the system, so it's cooling. As our system is cooling in the freezer, we are going to be moving down along this curve here. So temperature is decreasing, that means pressure also has to decrease. So because we're not adding any air and our volume is not changing, that's going to create a vacuum in our system because it's just going to be empty space, a vacuum. So as we move down along this curve and get closer to our triple point and our liquid is cooling, there will form a layer of ice above our liquid. And just above the layer of ice, there'll be a small portion of water vapor above that. So we're left with our triple point here, where exists water vapor, water as ice, and water as a liquid. So today we'll be talking about the Antoine equation and how it relates to a phase diagram of a pure substance. So as a reminder of what the phase diagram looks like, we have temperature on the x-axis, pressure on the y-axis, and it's going to look something like this, with this as our triple point, and this region is going to be a vapor, and this region will be a liquid, and this region a solid. So if you're looking at the phase diagram here, you can see we go along this curve here. As our temperature is increasing, our pressure is also increasing. So this relates to our Antoine equation, which is going to give us a relationship between temperature and pressure. So our equation is going to look like the log base 10 of pressure is going to be equal to A minus B over C plus T. And you're probably wondering what A, B, and C are. They're just constants, they're just numbers. They are going to differ based on what substance you're looking at and what temperature. One thing to note with this equation is that units of pressure and temperature are very important. So temperature is always going to be degrees Celsius. Pressure is always going to be millimeters of mercury. With our phase diagram, we usually read it in atmospheres, so a quick conversion from, so 1 atmosphere is going to be equal to 760 millimeters of mercury. So with the Antoine equation, we're given temperature. If we're given temperature and pressure data, our goal is to then find the constants for that substance. And we can also solve for P, pressure, if we know A, B, and C, the constants, and temperature. Vice versa, we can solve for temperature if we know the pressure. The first way that we're going to look at this is with nonlinear regression. So we're going to use something called a sum squared error, usually abbreviated with SSE. It's pretty simple. For now, we're going to assume that we have some kind of graph here that has a straight line model. This is our x-axis, y-axis. We're just going to say that it equals y equals mx plus b, where m is our slope, b is some constant. Usually when we get data, they're not going to lie right on our model. We're going to have points that are a little off, and this is how we're going to relate this to sum squared error. So our sum squared error is going to be the difference between our data values and our model line that we want to fit. So the equation we're going to use to find the sum squared error is going to be, so sum squared error is going to be equal to the sum of your index starting at 1 all the way to your n number of data values. And the general equation in here, universal equation we're going to use is y minus yi squared. So our y value is going to be our equation here, so we can substitute that. So again, we have y, or the sum of the index 1 to n of mx plus b minus yi, and all of that is going to be squared. Now you're probably wondering why it's squared, and that's because if you see some of these data values here fall below our model line, so that difference is going to give us a negative number. And we're not really worried about if it's positive or negative, we just care about the total difference from our model. So our goal in doing all of this with the sum squared error and everything is going to be to minimize the difference from our data values to the model. We're going to looking back at the Antoine equation, we have pressure and temperature, and we want to minimize what the data says in our values for A, B, and C. This cannot really be done by hand, easily. So we are going to be coding this in Python, and we will be making guesses for A, B, and C to determine the approximate values of our constants A, B, and C for a specific substance. So my cat has come to join me. Here she is. So now that we finished talking about the sum squared equation function and with the Antoine equation to find A, B, and C, we can now code it in Python. Get out of here. So first we need to bring these temperature values here and pressure values here into our code. So we're going to use a command called wget, which is going to bring everything from a website onto your code. But this is way too much information on this page than we need, so we can click raw and it will just give us the temperature and pressure values that we need. So we'll go ahead and bring that into our code. And there we go. So now we want to bring things from other modules into our code. So we're going to import numpy as np. And we also need the minimize function from scipy. So we're going to do from scipy optimize, because it's an optimizing function. We want to import minimize, and then to be able to plot our graphs at the end, we're going to need to import stuff from Plotly. So from Plotly dot subplots, we want to import make subplots. And we're going to need other things from Plotly also, so we're going to go ahead and import Plotly as PIO. Make sure that's good. All right. So now we can go ahead and look at our data that we have. So what we're going to do is np load text. And then we need to define what the name of the file that we're getting the data for, and see it's right here, water vapor pressure CSV. So we're going to copy that and bring it down here, and if we just run it like this, it's going to come up with an error because it can't convert the string to a float. It doesn't recognize the comma separating these data points. So what we need to do is identify the delimiter as a comma. So now it will give us our values in two columns, temperature on the left and pressure on the right. And we can go ahead and call that our data. So now we can identify temperature and pressure values to be able to separate those out and use them in our equations. So we can say temperature is equal to data, and here, let's pull up the data again. So if you can see here, we want, for temperature, we want just the left column. And it doesn't matter which rows, we want all the rows, so we'll use a semicolon to identify every row. And then for indexing in Python, it always starts at 0, even though it should be 1. So we'll say 0 for the first column. And then, oh, I forgot to define this as data. Here we go. Now we want to identify pressure. So we say P equals data, and again the semicolon, and it's going to be 1 since it's in the second column. So now we can go ahead and print these, and they will be separated for us. So if you remember from the Antoine equation, we have a log base 10 of P in the equation. So we can go ahead and change that to be log 10 of P, and then we need to do numpy log 10 of these values, so that it will do that calculation for us and automatically change those values to be the log base 10 of the pressure. So now if we hit Shift Enter, see those pressure values have changed. So now we can go ahead and start setting up our sum squared error function. So we'll call it SSE, and we need to define some kind of vector. We'll just call it V, and we need to define this function here. So here we have that, and we can go ahead and unpack this V vector and call it A, B, and C is equal to V, because those are the values that we will be guessing, so we can input those values and get a return of our sum squared error. So now we can go ahead and write out the Antoine equation. We have log 10p is equal to A minus B divided by C plus T. But what we want to return is the difference between our right side of the equation from the left side, so that way we can get the difference from our guessing ABC values from our actual data values. So what we're going to want to do is subtract the log base 10 of P from both sides, so that way we can get that difference. And if you remember, we don't care about the negative values, so we can go ahead and square this whole thing. Oops. And that will give us only positive values for our error. So right now we just have the error of one set of data points, so we need to find the sum of these errors. So we're going to do numpy sum to calculate the total sum of the errors. And this is what we want to be returned, so we'll say return. Shift Enter, make sure it's good, and it's not. Oh, I forgot a colon here. Alright, so now we're set. So we can go ahead and define some vector to start guessing our A, B, and C values. So we can call it G for guessing, why not? And we're going to input, I'm going to guess 1, 2, and 3. And in the future, once we bring in the minimize part of this process, if your guesses are really far off it can really affect your results and give you a really skewed, incorrect, inaccurate answer. So make sure you're using at least realistic guesses. I've run this before with 1, 2, and 3, so I'm fairly certain that it should be fine. But let's go ahead and check our function of SSE with respect to G to see if it returns a sum squared error. And it does. So for these values, our sum squared error would be 686. So now what we want to do is minimize the value of our sum squared error to get it as close to 0 as possible, which would mean our A, B, and C values are as close to the actual model value that we're trying to get at. So to do that, we're going to minimize our SSE, and this is going to be comma G, and print that, and see it gives us all this information, but really all we care about is this X values down here of 10, 1756, and -36, because those are going to be our A, B, and C values. So to make this a little easier to read, we can go ahead and do .x to call upon that specific part. And it will just give us those A, B, and C values. So now we can go ahead and say that A, B, and C are equal to these values and define them. So now we can just say A, and it'll give us just A, or we can say A, B, and C, and it will print all of those values. So now that we've found values for A, B, and C, we can go ahead and plot our data values with the regression line. So I am choosing to plot both on the same chart, same graph, so we can view the relationship better, more side by side. So first, we need to fig equals make subplots. And then we need to add a figure. Subplot, or sorry, scatter. We want to add a scatter plot. And this is where we're going to include our raw data values. So we're going to have X as temperature. Y is going to be our log base 10 of pressure. And we need to set up the mode. In this case, we should use markers so that we can see the individual data points on our chart, on our graph, instead of a line. And then we can give it a name. So we can call it raw data. And shift enter to see what it looks like. So here is our graph of our raw data points. So now we can go back in here and add another plot. So fig.add another scatter plot. So this is going to be our graph of our regression line. So our X is going to remain as temperature. Our Y value, though, is going to change because for our raw data, we were using the log base 10 of pressure. That was our original data values. But in this case, for the line, we need to use the values that we obtained, A, B, and C, from minimizing our SSE function, which we subtracted our log base 10 of pressure from our Antoine equation, A minus B over C plus T. So if we are looking at just the regression, we want just the Antoine equation. So we have A minus B over C plus T. Oops, forgot some parentheses. And then the mode for this graph is going to be lines. And we can name it nonlinear regression. And we'll go ahead and graph that. So here we can see our individual raw data points, labeled raw data over here, and the nonlinear regression line through them. So you can see on this graph here, there are a few harsh straight lines, like here between 343 and 412, and again over here between 571 and 647. There is a way that we can minimize that. Instead of using the temperature points that were given to us, we can add some evenly spaced temperature values to even out that line a little bit so it's not so harsh and straight. So what we're going to do is say t plot is equal to numpy linspace, which is just the command that we're going to use to do this. So first we need to define the lowest temperature value. So we look at here on our chart, 293 is our lowest temperature value that's given to us. So we need to make it something slightly lower than that so it includes that point in our plot. So we could say like 280. And then for our maximum temperature value, we can go over here and see it's 647, so we can just say 650 is our maximum value. Then we need a number of points, so we'll just say 1,000 points. And then we need to go down here and make sure these all say t-plot instead of just t, so that it will change our actual nonlinear regression curve. So if we see that now, it is much more curved, it's not as harsh, and this gives us a evenly spaced number of temperature values instead of just the given data values that we had before. And if you want, we can see the difference here between what we did and how it was before. So if we just bring that down again, change this back to temperature with the given temperature values that we had, then we can see, if you zoom in here, there is a bit of a difference. So how do I get back out? Let's see. Okay, so we don't really need that one anyways. We can just get rid of that. And here we're left with our final plot using nonlinear regression to find our Antoine equation. So now that we've solved for A, B, and C using nonlinear regression and sum squared error methods, we are now going to use linear regression to solve for A, B, and C. In this method, we'll be using matrices, vectors, matrix multiplication, design matrices. So if we look at Antoine's equation again, we have log base 10 of p is equal to a minus b over c plus t. So for this linear regression part, we want all of the unknowns to be on one side of the equation so that we can express it with matrix multiplication. So all of them are on one side right now, but an issue that we have is that one of our unknowns, c, is in the denominator. So we're going to have to multiply that out and get a common denominator. So we will have C plus T log base 10 of pressure is equal to A times C plus T minus B. So now the next step is just to multiply everything out. So we have C log base 10 pressure plus T log base 10 P is equal to AC plus AT minus B. So now we almost have all of our unknowns on one side, but there's this C left over here that we need to bring back over. And again, our pressure, temperature is already known, so we can leave that together. So I'm going to bring these over here. So we have AT minus C log base 10 of P plus AC minus B is equal to T log base 10 of P. So now that we have all of our unknowns on one side and our knowns on the other, we can set up a matrix multiplication to express this. So first what we're going to do, set up our matrix. Alright. And here we are. So in this first column, if we look at the equation here, we'll have temperature. So we can fill in T1, T2, T3, all the way down to Tn. And the second column, we're going to have log base 10 of pressure, but if you notice here, can't forget the negative sign, so we're going to have negative log base 10 of P1, negative log base 10 P2, negative log base 10 P3, and again all the way down to negative log base 10 P to the N. And since we have our unknowns, we'll fill in this column with 1s here. And so in this next matrix over here, we have our unknown A first, then we have C, and then here we have this little fun thing. We can easily just make this a variable, call it D, just to make it easier. So we'll call that D. And then on the right side of the equation here, we have T log base 10 of P. So that's going to be just T1 log base 10 P1, T2 log base 10 P2, and again so on Tn log base 10 of P to the N. So now that we have our design matrix, we can see that here we have a n by 3 matrix, we have a 3 by 1 matrix, and a n by 3 matrix. N by 1 matrix. So to make this much simpler and easier to solve for us, we can define variables to these different matrices. We can call this one Q, we can call this one U, we can call this one B. So then we have Q, U equals B. But in order to solve this, we need to take the transpose of Q. So Q transpose times Q U is equal to Q, the transpose of Q times B. And now we're left with 3 by 3 for these, a 3 by 1, and a 3 by 1 matrix. So now we can set these matrices up in Python and let the computer do the solving math part for us. So now that we've figured out how to solve this using linear regression, we can go ahead and set this up in Python. So we can start with our first matrix, Q. Say that Q is equal to, we're going to use NumPy and the concatenation of this matrix. So in our first column, we're going to have the temperatures, so T. In our second column, we have the negative log base 10 of pressure. And then in our third column, we have the column of ones, but in Python, we have to write that as NumPy ones like T, which basically just means every time there is a T in the first column, there will be a 1 in the third column. So if we go ahead and print that out, make sure that works. Here we go. We have temperatures here, negative log base 10 of pressure, and a column of ones. So our next vector that we can define is our B, but since we already have a B up here for our nonlinear regression, we can name it something else. I'm just going to call it S. No real reason, just another variable. So that's going to be equal to the temperature times the log base 10 of our pressure. So then if we print out these values, we have our S, S. These are our values for the right side of the equation. So now, looking at this equation back up here, we have the Q transpose, which is just Q dot T, and we are multiplying a matrix by matrix. So we use the @ symbol, and that's going to be multiplied by our Q matrix. And then we're going to have on the right side of the equation the Q transpose, again QT, and it's matrices multiplication, so we use the @ symbol, and that's going to be multiplied by our S. And if we shift enter, we can see that we have a 3 by 3 matrix here and a 3 by 1 matrix here for the right side, which is what we expected to get. So now what we have to do is get Python to return us variables for A, C, and D. And to do that, we're going to use NumPy linear algebra solve. When we do this, we don't need to include the vector ACD in this command because Python already knows to output those variables. So we hit shift enter, that gives us value for A, C, and D. And if we compare our A and C values from up above, we have 10.2 and -34. Up here we have 10.2 for A and -36 for C, which is very, very close. So now that we have those values, we still have this D here and we want to find B. So what we're going to do, we know our equation. Well, first we need to unpack this equation. So we can define our variables, A, C, and D, but instead of using A and C, we can use A2, C2, and D2, just so it's less confusing and we're not confusing those variables with the ones we used up above with our nonlinear regression. So now we go down here, we know D2 is equal to A2 times C2 minus B2. But B2 is the variable we want to solve for in this case, so we can just flip this around and say that instead of D2 equals, we'll say B2 is equal to A2 times C2 minus D2. And now we print E2. We have a value of 1771.9. If we compare it 1756, that is also very close. So now what we have left to do is just plot it. So I'm going to come up here and just copy this down so I don't have to retype it because most of it will stay the same. So we need to make these Fig 2. And then we're still going to have our data value markers plot with those data points. Those are going to stay the same, so we can leave that how it is. Our t-plot lens space from 280 to 650 with 1,000 points is also going to stay the same, so that way in our new plot with the line we can get this nice curved line that is the general form of the curve. The only thing we do need to change here is our A, B, and C values because these are still coming from our nonlinear regression points. We need to make them for our linear regression now. So we can call them A2, B2, and C2. And we'll go ahead and rename this to linear regression. And we'll plot that out. And you can see both graphs are almost identical. If you want a closer look, you can even bring this copy and paste it down here. Make this a Fig 2. So we're on the same graph, and that's going to be our nonlinear regression, and we'll compare it to our linear regression. So as you can see, they're right on top of each other. You can not even see the linear regression line from this chart. We would have to zoom way in. You can start to see it. Here they're almost overlapping, like 0.005 off from each other. So they are very close. So that is the end. We've discussed how to use Antoine's equation to find values for A, B, and C given water vapor pressure and temperature using nonlinear regression with the sum squared error method and the linear method with matrices. Thanks. So today we're going to be talking about how to get at the final temperature and total volume of a system when we're given values for initial and final conditions. So we're going to start out with an open container, and it's going to contain some liquid, and it's going to have a small amount of vapor above that liquid with just air above that. We're going to go ahead and seal this container and heat it with the rest of the remaining air left inside. And what we're going to do is want to find the final temperature and the total volume of our system. So we can start out by listing out some known values that we're given. We know the initial pressure is going to be 1 atmosphere, which is 101,325 pascals. And we know our initial temperature is going to be 298. And we know our final pressure is going to be 200,000 pascals, which is the same as 2 bar. We also know that our mass of water in the vapor phase is going to equal, the mass of water total is going to be equal to 1 kilogram. And we also know the number of moles of our water in the vapor phase is going to be equal to 0.3 moles. And we can also write this as a represented with density. So we can say that this moles of water vapor is equal to the mass of our water vapor divided by 18 times 10 to the negative third kilograms per mole. I'm sorry, I made a mistake. This is not in terms of density of water. This is the molecular weight of water. So we can use the number of moles of our water vapor and the molecular weight of water to determine our mass of the weight of the water vapor, the mass of the water vapor. So we are going to be bringing in some equations that we already know to solve for our final temperature and total volume. So we're going to be using just the symbols here in our equations instead of plugging things in, because that'll just make it easier when we go into code our equations later. So we can start with volume. So we know our total volume is going to be equal to our volume of our vapor plus the volume of our liquid. Then we also know that the mass of our water total is going to be equal to the mass of our water as a liquid plus the mass of our water as a vapor. And since over here we can solve for our mass of water vapor and we know our total mass of water, we can use that to substitute and solve for mass of water as a liquid. So now if we think about pressure, we know that temperature has an effect on pressure. So as our pressure has increased, our temperature has also increased as well. So we can unpack our pressure values to find our variable of final temperature. So we're going to start with our final pressure is going to be equal to pressure of the air plus pressure of the water. So our pressure of the air is going to be, so we're going to assume that this is an ideal gas because we don't know how to do it otherwise, and that way we can use the ideal gas law to determine what our pressure of our air is going to be. So it's going to be the number of moles of water vapor times R times our final temperature divided by our volume of our vapor. And so that's going to be our pressure of air, and we will go in, oh, I'm sorry, this should be up here. Not. So now we can look at the pressure of our water, and if you remember from Antoine's equation that our liquid water is going to exert vapor pressure up and increase the pressure and at a given temperature. So our Antoine equation is going to look like log base 10 of our water pressure. It's going to be equal to A minus B over C plus our final temperature. But we can just go ahead and rewrite that in terms of our pressure of our water. So we can set that equal to our water pressure. So we can say the pressure of water is equal to 10 to the A minus B over C plus our final temperature. So now we have two places where our final temperature will exist in this equation that will influence our final pressure, which is one of our known values. So now we're going to talk about our volume equation up here. So we're trying to get at our total volume. We don't yet know how to solve for our volume of our vapor, but we can pretty easily come up with equations to solve for our volume of a liquid. So we're going to start using density of water to simplify this because density is mass over water. So we can say density of our water as a liquid is going to be equal to our mass of our water as a liquid divided by our volume of the liquid. And you can see from our masses equation over here, mass of water liquid, we can solve for that by doing a little subtraction. So we can substitute that in here and say, or why don't we go ahead and rewrite this and set it equal to the volume of our liquid. So volume of our liquid is going to be equal to the total mass of our liquid, of our water, sorry. The total mass of our water minus the mass of water as a vapor divided by the density of our water as a liquid. So from this, we can easily plug in our volume as a liquid into our equation up here, so we can have one step closer to solving for our total volume. So now that we have our volume of liquid, we can go ahead and solve for our volume of a vapor. So if we look down here, we see volume of our vapor is in this pressure of air equation here. So what we're going to do is go ahead, set up an equation to solve for the number of moles of air in this equation. So this is going to look like number of moles of air equal to, and we're just going to be using the ideal gas law again, like up here, but we're going to set it up as the initial state of our system. So that's going to be the pressure of our air initially times our volume of our vapor divided by R times our initial temperature. So now we can go ahead and further unpack this and say our initial pressure of air is going to be our initial pressure minus our pressure of water at the initial temperature. And our volume of our vapor we can get from substituting in this equation up here and say our total volume minus, and we have defined what our volume of our liquid is here, so we can substitute this in here and say minus our mass total of our water divided by the density of our water as a liquid. And in this case, we don't need to worry about the mass of the water as a vapor because initially it is such a small amount that we're just going to ignore it. And then it's still all over R times our initial temperature. So lastly, we're going to include one more equation that's going to be another ideal gas law that we might need. And that's going to be our number of moles of water vapor. So we have moles of water as a vapor. And that's going to be equal to our pressure of water at the final temperature times our volume of our vapor divided by R times our final temperature. Now these are all the equations that we are going to need for this problem, and we can go ahead and plug them into Python to code it out for us. So now that we have all of our equations, we can go ahead and start coding this out in Python. So the first thing that we're going to want to do is grab information from our GitHub site. So to do that, we will do git, and we're going to want to clone this information to bring it into our Python code. So we'll specify with clone. So we'll go over here. We're going to want the data, which gives us data for different substances, and tools, which we'll be using in our code. So to bring this over, we just go to the green code button, hit copy, and paste it into our code. Now we want to also specify that we want the most recent data and information from this website. So to do that, we will do a depth of 1, shift enter, and it's saying that it already exists, which is fine because I've done this before. And here it is, we have our CHA tools, data, and tools. So now what we're going to want to do is import some other things. So we're going to want to import our system, and we want import system path insert, and this is just going to specify the path to Python that we want Python to use. So we're going to use 1, and that just means that we want our inserted file here to be the first place that Python looks for information. And then we can specify that we want it to come from CHE tools and in our content file. So to do that, we can just come over here and copy path and paste it in here. So then we also need to import our tools. Tools from CHE, we'll just call them CHE. And then we're also going, oops, not CHE tools. Okay, so we're also going to need to import some things from SciPy. So from SciPy, optimize, we want to import the root function. So should make sure that's good. We don't need that. There we go. Now we can go ahead and identify what our R value is going to be. And our R value is going to be 8.314. And we can't put units in Python, so we're just going to comment them out and keep them in here as a reminder of what those units are. So it's going to be joules per mole times Kelvin. So now we can go ahead and specify our P. So we're going to set this equal to our CHE tools. I'm sorry, not tools. Properties. And we want to specify to Python that we want to use the equations and functions for water. So that's what we're doing here. And now we can go ahead and start listing out some of our known values. So we know our initial temperature is going to be 298. Our initial pressure is going to be 101,325 pascals. And our final pressure that we're going to call P desired is going to be equal to 200,000 pascals. I'm skipping putting units in here, just assuming that everything is going to be in SI units. We also know the mass of our water total is equal to 1 kilogram, and the number of moles of water vapor desired that we are left with at the end is 0.3. So now we want to define our system of equations. So define our equations. We'll call this our vector v, and we can go ahead and unpack our vector because that's going to be our unknown values that we want to solve for at the end. So that's going to be our final temperature and our volume total. Set that equal to V, our vector. So now we can go ahead and start entering in some of these equations that we have. So first, we can set our pressure of the water. It's going to be equal to our P dot properties. I'm sorry. It's going to be our P, pressure of the vapor, of our final temperature. And then other equation, we have the number of moles of air. It's going to be equal to our initial pressure minus our pressure of the water vapor at our initial temperature, and that's going to be multiplied by our volume of our vapor phase. So before we unpack that and set it as our total volume minus mass of our water total, and divide that by our density. So that's going to be our P rho L of our temperature. I made a mistake here. This parentheses should be at the end. So next we have the mass of water in our liquid phase is equal to the mass of water total minus the mass of water in the vapor phase. We can go ahead and define our mass of water vapor up here. So mass of water vapor is going to be equal to our number of moles desired multiplied by constant 18 times 10 to the negative third. So here we have defined mass of water vapor, so we can use it in this function here. Next we have the volume of our liquid. Say volume of liquid equal to the mass of our water of a liquid as a liquid divided by the density. So that's again going to be the rho L of our final temperature this time. Now we can insert our volume of vapor equal to volume total minus our volume of our liquid. So we can do pressure air equal to the number of moles of air multiplied by our constant, multiplied by our final temperature. And we're going to want to combine these so we can divide the whole thing by our volume of our vapor. I need that capital O's, that should be lowercase. Okay. So next we'll define our pressure, our final pressure, to be the pressure of air plus pressure of our liquid. Alright, so that's going to be our PW, not P liquid. Next, we have our number of moles of water as a vapor desired is going to be equal to, that's going to be our pressure of water multiplied by our volume of our vapor divided by our R value times our final temperature. So now we can go ahead and write out our return function. So we want our function to return our final pressure minus our desired pressure. So we want to take the difference between our final pressure that we have calculated from these equations here and this function here, the difference of those, and we okay, so this is supposed to be our number of moles of vapor that we're going to calculate, and we want to do our number of moles that we calculated of vapor minus our number of moles of vapor desired. And the reason we are subtracting these is because we want to minimize that difference so that we can get a closest value of final temperature and volume total as possible. So run that and everything looks good. We can go ahead and do our root function. So now we can go ahead and make our root function, and we're going to bring in our equations, and we need to specify a guess of our final temperature and total volume so that Python can run it and calculate our actual final temperature and volume total. So for final temperature, we can say something like 350, and our total volume, we can say 1, add the decimals so it doesn't. So here it says the iteration is not making good progress. So that means that we have a bad guess. So I'm going to change the total volume guess to be 0.1 and see if that helps. Still no. So I found my error. I forgot to include this divided by R times temperature initial, and this wasn't in parentheses. So let's run it again and see if that helps anything. So here we go. These are the correct. So I'm going to call out these values here. So our final temperature is going to be 366 Kelvin, and our volume total is going to be 0.0126.